Okay, this is one of my favorite examples to work through. The question here is, in order to avoid getting wet, is it better to walk or run in the rain? I love this example because it's a very practical question, and it's kind of vaguely written to start with. It's kind of a real world situation. I want to go from point A to point B. It's raining outside. Do I walk or run? And rather than just use your opinion, we want to actually justify our answer. If we're going to walk or run, what speed do we go at? Do we go at the speed of the horizontal projection of the rain speed, or do we want to go infinite speed? Do we want to go infinitesimally slow? We want to actually figure out what speed is the correct speed. And the way we'll approach this is we'll make the problem more well-defined. And again, this is part of the reason I love this problem, is because we're starting from a vague statement and we're going to make it more well-defined. So let's go ahead and do that. So the picture we're going to deal with is this. Here is the person, so this is me, and I'm trying to get over to this house. So I want to get out of the rain. And I'll say that the distance I'm traveling is L. Okay, so I'm starting to make the problem more well-defined here. I'm saying this is a flat surface that, we're in Indiana, so it's nice and flat. So I'm not going uphill, I'm not going downhill. And I'm saying I'm a distance L away. I'm going to say that I'm moving at a constant speed v off to the side. That's what we're going to try to figure out, is what value should v have. I'm going to say the rain is coming down at some angle with respect to the vertical. Let me just call it theta. And it comes down at a constant speed v rain. So my velocity v and the velocity of the rain I'm going to assume are both constants. Same with the theta. So it's just again, I'm making it well-defined, kind of simplifying it here. And give me a second here, there we are. And if you think about this for a moment, what I'm trying to do is minimize the amount of rain that accumulates on my body here, right? I'm trying to minimize the mass of rain that accumulates on me. So this is a conservation of mass kind of problem. So I'm going to want to apply conservation of mass. So I'll write it out, and then we're going to evaluate it. So that first term is the time rate of change of mass inside the control volume. Second term is the mass flow rate term. It's the net mass flow rate out of the control volume. And since I'm applying conservation of mass to a control volume, I need to identify what my control volume is. And the control volume I'll use will be one that surrounds me, because that's where I want to minimize the amount of rain mass that I'm accumulating. So let me put some dimensions on this. We're going to say that this area, when looking from above, we're going to call it A top. It's the projected area when you look down from above. And then from the side here, we'll call it A side. So that just puts some dimensions on my control volume. So let's go ahead and start evaluating some of the terms in conservation of mass. And we'll talk about a couple of additional assumptions along the way. So the first term is just the time rate of change of mass in the control volume. And again, we want to minimize the amount of mass in the control volume, so we'll get to that later. The next term is the mass flow rate term. So we're going to evaluate that in just two locations. So the first place we're going to evaluate is right along the top. We're going to evaluate how much mass is coming in from the top, and then the other place we'll do it will be on the side, just the front side. I'm not going to worry about the mass flow rate of the rain coming in through the bottom, because I'm not going to worry about any puddles or anything like that, so we're not splashing through puddles on our way there. And I'm not going to worry about any rain mass coming in from the back side or in and out of the page, because I'm not going to worry about vortices that carry the rain and it kind of swirls around on my back and gets me from behind, or same thing from the sides. So again, these are assumptions I'm making. They're very reasonable ones, but they help keep the problem well-defined and manageable to solve. Okay, so I'm only worried about the top and the front side. So let me evaluate that term from the top. So the density that's coming in will be the density of the rain. So the rain's coming down with some density. That's basically just the mass of rain per unit volume. So it'll have to do with the size of the raindrops and how well spaced they are, that kind of thing. Now the relative velocity, let me remind you, the relative velocity is the velocity of the fluid minus the control surface velocity. So let's evaluate both of those. The velocity of the fluid, well, if I'm going to do these velocities as vectors here, I should put a coordinate system. So let me do that. We're going to say this is our y direction and this is our x direction. And since I'm doing that, let me put the components of the rain in those directions. So this will be v, give myself a little more space here. This will be v cosine theta vertically, and then this is v sine theta horizontally. So the velocity of the fluid, or the velocity of the rain, will be a minus v sine theta in the I hat direction, minus a v cosine theta in the j hat direction. And this should be the rain, velocity of the rain. Right, so this, what I'm doing is I'm evaluating the velocity of the fluid. That's the rain. And I have a minus v sine theta, or v rain sine theta. It's minus because it's in the minus x direction. And then I have the minus v rain cosine theta here. That's this vertical component, and again, it's in the minus y direction. So that's just u fluid. Now I have to subtract out the velocity of my control surface. Well, the control surface is just moving horizontally at a speed v in the positive x direction. So that'll just be a v I hat. Right? V I hat because this control volume and the control surface are moving in the positive x direction at a speed v. So that's what that term is. And so this is all my relative velocities, or my relative velocity term. Now I'm going to do the dot product with the area. Now the area I'm interested in here is the area at the top. So the magnitude of that area is a top, but remember this is a vector, so I need to put a vector on it. So I'm going to use my outward pointing normal vector. So on the top, the outward pointing normal vector n hat is pointing upward, so it's in a positive y direction. Again, it's an outward pointing normal vector there. So it'll be a top j hat. So that's everything that we have for the top. Let's go ahead now and evaluate what's happening on the side. So there, the density of the rain is still rho rain. The relative velocity is exactly the same as what we had before. The velocity of the fluid is still the rain velocity that we already wrote down. And the velocity of the control surface is still just the v I hat like we had previously. So we'll go ahead and write that in the exact same manner. Okay, so the relative velocity is the same, but the area now is different. So the area on the side, the magnitude is a side, and the normal vector, outward pointing normal vector, is in the positive I hat direction, right? Because it's pointing outward in the positive x direction. So that area will be a side I hat. All right, and again, we're ignoring what's happening at the bottom of the control volume. There are no puddles. We don't worry about what's happening on the back or the front and back faces because there's no swirling of the rain, we're assuming. All right, so now let's evaluate our conservation of mass statement. Here's our time rate of change of mass inside the control volume. And we have I'm going to evaluate this first expression through the top. There's my density of the rain. When I do remember there's a dot product here. When I do the dot product, it's only the j hat that I have to worry about because the area only has a j hat component. So it's just going to be this part of the velocity that remains because of the j hats. There is no I hat to dot product with. So we'll get a minus v rain cosine theta times a top. So that's what we get from that term for the top. Now let's do the term from the side. Now in this one, it's the I hats that I'll care about because the area of the side has an I hat vector. So I'll have to take into account that I hat term and this I hat term. So let's write those down. So I'll have a minus v rain sine theta and a minus v all times a side. So here's the minus v rain sine theta right there. Here's my minus v right there, and then A side is right there. And then all of this sums together to equal 0 from conservation of mass. All right, things are looking good. Let's go ahead now and simplify that equation. I'm going to just keep the time rate of change of mass and the control volume on one side. I'm going to bring the mass flow rate terms to the right-hand side. I'll pull the density of the rain outside since it shows up in both of those terms. And then I'll have V rain A top cosine theta. That's this term. It's positive because I'm bringing it to the right-hand side. And then I'll have plus V rain sine theta plus V times the area of the side. So that's this term. The negatives become positives because I'm bringing it over to the right-hand side. So this is what we now have. All right, so far so good. Let me go ahead and solve this differential equation. I'm going to keep the dm CV term on the left-hand side. I'll bring the dt to the right-hand side. Okay, so we have that, and then I'll just integrate both sides. Okay, so I'm going to say that I'm initially dry, so the initial mass inside the control volume will just be, the mass of the person. Right? So that's just the mass of the person inside the control volume, and the person plus their clothes. We're going to assume the person's dressed as they're running there. So you know what? Instead of just mass person, I'm just going to put m naught. So that's the mass of the person and their clothes. They're initially dry. And then at the final state, it'll be the mass of the person and their clothes plus some change in mass because of the mass of rain that's accumulated on them. It's the delta m that I'm trying to minimize here. And then on the other side, the time will be initially, we'll say it's 0 time. And then the final time will actually be the time it takes for the person to go from here all the way over to there. So remember, we're traveling a distance L, and we're going at a speed v, so the time that it takes to travel that distance, capital T, will just be L divided by v. Right? It takes some time to get, travel this distance L. So we're assuming that we're going a constant speed v, so it'll just be capital T there. So I'll just write it as L over v. All right. Well, when we evaluate the integral on the left, that's pretty straightforward. That just comes out to be delta m. And then when we evaluate the integral on the right, just keep in mind that everything in here is a constant. Density of the rain, we said, was a constant. The velocity of the rain, the angle of the rain, those are constant. Area of the top and the area of the side, we're assuming are constants. We're not contorting our body as we're moving along. And we said that we're traveling at a constant speed. So those are all constants. So this just becomes the following. So that's what we ultimately get when we do the integral. Let me simplify this just a little bit further. We're going to just multiply through by the L over V. And yeah, let's do that. We have V rain A top times L cosine theta, all divided by V, plus V rain sine theta times L. We put the L in there. And there's an A side there as well. Divided by V, plus, then we'll have L times A side. All right, I think I did all my algebra correctly there. Let me just double check. Okay, I think everything looks good there. All right, so here we are. This is the amount of mass that is accumulated on us due to the rain. We're trying to minimize that. And then this is everything else. This is all related to the mass flow rate. So we're trying to minimize delta M, and the only thing that we can control is the velocity. Okay, so if you look at that for a second, to minimize delta M, what we want to do is make the velocity v as large as we can. Right? We want to make v as large as we can. In fact, we want v to go to infinity. Right? Because if v goes to infinity, then these terms become 0, and all we're left with is one term here. So bottom line is, if it's raining and let's go back up to the picture. If it's raining and you're trying to get, from point A to point B here, you want to go as fast as you possibly can go. Run as fast as you can go, and that will minimize the amount of rain that accumulates on you. Okay? But if it's interesting, if you look at this, there's a constant value here. Even if you go an infinite speed, you still are going to get a particular amount of rain. In fact, let's write that out. So if in the limit, delta M as v goes to infinity, what you're left with is density of rain times L times A side. There's a certain mass of rain that's going to accumulate on you. Right? And what this term is here, the L times A side, that's actually the volume that you carve out as you travel this distance. Let me redraw it down here so it's a little clearer. So here you are, and here's the house. This is the distance L. And what's happening is you're trying, and this, by the way, is your area of the side. Let me redraw the area of the side since that shows up in the equation. Okay, so what this term represents here is the volume that you carve out as you run through the rain. So it's this volume. I'm just going to show it right here. That volume is L times A side. So the idea is this. If you could run at an infinite speed, all those raindrops look like they're basically frozen in place, right? You're going so fast that the raindrops effectively look like they're stationary. They're not really moving. And because they're stationary and you're running super fast off to the side, you're just going to carve a tunnel through the raindrops. And that tunnel that you carve out will have this volume, and then you multiply it by the density of the rain, and that gives you how much rain you've actually accumulated as you've gone from point A to point B here. So you'll always get this amount of rain that accumulates on you, even if you run at infinite speed. Now the reason you want to go at an infinite speed is because, you're trying to minimize these terms. What these terms represent are the following. So this one, let me start with the second one here. This term is the additional rain you would get if you weren't going super fast and you were actually kind of going at a slow speed through the rain. Then you're still going to get raindrops. Remember the rain's going like this, and it has a horizontal component, v sine theta. What you're going to do is you're going to get extra raindrops because they keep coming down. They're moving relative to you, and you just keep getting additional raindrops coming in from the front. So that's what this is the additional raindrops coming in from the front if you walk slowly. This one refers to the additional raindrops, or all the raindrops that are coming in from the top, right on top of your head, right here. So again, if you're spending time, if it takes some amount of time to go from point A to point B, you're getting lots of additional raindrops coming in on your head. And that's what this term is all the additional raindrops on your head. If you go in infinite speed, you don't get either of these because effectively the raindrops are frozen in place. Nothing's going to come on top of your head, and no additional drops are going to come from the side because all these raindrops are just frozen in place. You'll just still carve out your tunnel, but that'll be it. So what we did to just kind of recap this problem as we started with something very general here. Is it better to walk or run in the rain? What we did is we recognized, oh, this is a conservation of mass problem. So we said we're going to apply conservation of mass, so we had to draw a control volume. Then we had to make the problem more well-defined. We're saying it's a flat ground, the rain's coming into our face at an angle theta, there's a distance L we're traveling, constant speed. We only worry about rain through the top and the side, or front side. All those things are constants. And then we solved our conservation of mass statement. We went ahead and dealt with the relative velocity terms, the area terms, evaluated the dot products, solved all that, solved the resulting differential equation, which gave us this expression, ultimately this expression. And then we analyzed this to see how we could minimize delta M, which showed us we should make V go to infinity. And then what we did is we thought about physically, what does that mean when V goes to infinity? What does that actually mean? And that's where we got this idea of, oh, we'll always get some rain accumulating on us because we're carving out a tunnel if we go at an infinite speed. So, we did our analysis and then brought it back to the real world through, an investigation of, kind of going through each term in this conservation of mass statement. So this is a typical procedure for real engineering problems. You start with something vague, make it more well-defined, solve it, and then go back and look at it and take the mathematics back into the real world and see what it really means. So that's why I love this problem. So I'm going to go ahead and end it there, but I want to just pose some other ideas for you. When I set up this problem, I had the rain coming into my face with an angle theta with respect to the vertical. Let me ask you this, and I'm not going to work through it. You need to think through it. What happens if the rain is coming from behind at an angle theta? Okay, so now solve the problem with the rain coming from behind you at an angle theta. Do we still want to go at an infinite speed v, or is there some other speed? What happens if the rain has an angle in and out of the page? So it's hitting us kind of on the front, from into the page or from out of the page. How does that change the problem? So think about those variations. The one where the rain comes from behind is actually a very interesting one, and I encourage you to think about that one on your own. Okay, we'll go ahead and end it there. Oh, actually, before I end it, let me just say that this problem has actually been looked at experimentally by Mythbusters. So there are actually one video on Mythbusters where they did this experiment, and they found in their video that you actually would be better off walking rather than running, and which they were very surprised about. They weren't expecting it, but then they revisited that problem, that experiment later, and then when they revisited it, they realized they had made some mistakes in their experiment, and when they revisited it, they realized, oh, you should run in the rain. So there is a video from Mythbusters, but keep in mind that they revisited that problem later and changed their answer. And there actually have been some papers that people have published on this exact same problem, just showing kind of the analysis. To be honest, I haven't looked through how they did their analysis, but I assume it's an analysis very similar to what I did here. So it's a problem that people have actually looked at in popular culture as well as in some journal publications. All right, now we'll end it there.